Hello everyone, in this video we'll be looking at how to simplify expressions, especially when dealing with equilibrium expressions. So the questions that we have to look at here today are, what about liquids and gases? How do they interact with each other when they're in an equation? And I should have actually included solids on here as well. We know from our class notes that liquids and solids are not included in these expressions. Okay, so this video focuses mainly on liquids and gases, but it could apply for solids as well. So just remember, solids can also be excluded, solids are also excluded from our equilibrium expressions. So we're going to be looking at how does this affect the overall expression, and are there ways to simplify the equation. So let's jump right into it. So if I took the standard equation of 2a plus 3b is in equilibrium with 4c plus 1d, all in gaseous form, all as gases, I could write an equilibrium expression that looks something like this. KEQ equals, and remember it's products over reactants, so it's C, okay, our concentration of C raised to the power of 4 multiplied by our concentration of D raised to the power of 1, because our coefficient here is just a 1, and then it's a ratio. Okay, KEQ is always a ratio, so it's going to be divided by the concentration of A raised to the power of 2 multiplied by the concentration of B raised to the power of 3. Okay, so that's our standard KEQ expression based on this sort of fictitious equation. Okay, so A, B, C, and D. So what happens if we don't have gases? So let's scroll down here and look at our first example. In this equation here, we see A and B are both liquids, and they're reacting in equilibrium to give C, another liquid, and 2 moles of D, which is a gas. So when I go to write the KEQ expression for this, I'd go KEQ equals, remember, products over reactants. We don't include liquids, okay, so liquids and solids are not included. So we don't include C, but we do include D, because that's a gas, okay, gas or G, and aqueous, AQ, always included in KEQ. So I'm going to write down D, and our coefficient there is 2. So it's the concentration of D raised to the power of 2 divided by, and I can't just leave it as 0. Okay, because we know that anything divided by 0, that's going to throw errors. So we look at our left-hand side of the equation, and even though they're both liquids, we would just represent it as a 1. Okay, and then we also know from math, if I gave you something like 2 over 1, that would actually just be 2 if we simplified it. If I gave you 1,000 over 1, that would just be 1,000. Okay, because anything divided by 1 will equal the original term. So in this case, the concentration of D raised to the power of 2 divided by 1, well, you know what? That is just the concentration of D raised to the power of 2. Okay, so nice and simple. That means we don't need this big piece here in the middle. KEQ is just equal to the concentration of D to the power of 2. What happens, though, if our terms are on the reactants and we don't have anything on the product side? So that's our next equation here. So let's look at this one really quick. I'm trying to keep this video short. Again, KEQ, always start by writing KEQ equals, and this is going to be a ratio. Okay, so products over reactants. When I look at the products of this equation, they're both liquids. That means they're not included. So I'm going to represent that as a 1. When I look at the reactants of my equation, I have the concentration of A. Okay, so the concentration of A raised to the power of 2. And you know what? It's going to be multiplied by 1. I'm just going to throw it in there just to make things nice and clear for this example. So I look at this and it's kind of messy. We don't need to show all of this right now, so we can try to clarify it, okay, or simplify it, sorry. So our numerator stays the same, and our denominator would just come down to A to the power of 2, because anything multiplied by 1 is just going to equal the original term. Okay, so A to the power of 2 times 1 is going to equal A to the power of 2. But then you may not like this, or you may see an example online or in a video where you don't have this numerator with a value of 1. And you may actually see something like this, where it says A to the power of negative 2. Okay, so that's one of our exponent laws coming in from our math class here. So if I do something like this down here, I could say 1 over x, and let's say x is to the power of 2. Well, you know what? When I use my exponent laws, that's equal to x to the power of negative 2. That negative sign, when it's an exponent, tells me that it's actually in the denominator. Okay, so we can actually simplify this equation and say KEQ is just equal to A to the power of negative 2. Okay, so KEQ is just equal to A, the concentration of A, to the power of negative 2. We've seen this concept of negative signs in past units as well, especially when dealing with concentration. We may understand concentration as moles per liters. Well, you know what? We can represent that liters on the numerator by going moles multiplied by liters to the minus 1. Again, there's that minus sign representing the exponent, and by using a negative 1, it actually tells me that liters is in the denominator of this unit. So it's just something to watch out for. This is something I want you to aim for. This will make you stronger with this equilibrium and stronger with the math of what's to come. So just pay attention to that negative sign as a way to take stuff out of your denominator and simplify it to a single line. All right, thanks.